So, we will now move on to what probably is a very fundamental aspect of looking at fluid flows. We have looked at flows where there was no vorticity. We looked at potential flow. We looked at viscous flows, but they were steady. And then we also looked at unsteady viscous flows. So, now the part which we are going to now get into is when we will look into aspects of what would be the role of convective inertia that is there in the problem. But before we get into looking into that equations and working with the math of that equation, I mean, it's important to just recall what we have done in our potential flow lectures. So, one of the problems that we solved in potential flow lecture was flow past a circular cylinder. We all did this calculation considering that the flow is potential, and as a part of the calculation we computed what is the pressure coefficient, which is P minus P infinity by half rho u infinity square, and that was 1 minus 4 sine square theta, where theta was basically measured from positive x axis. And if you recall, so here that you see pressure, so pressure is basically scaled by P infinity here, so it's like Cp that you are observing, and on the x axis is degree from the forward stagnation point. So, that is like pi minus theta. So, theta equals to 0 is basically the point A. So, this is point A. Theta equals to pi by 2 is your point B, and theta equals to pi is your point C, and then you move to the bottom hemisphere. So, the dark line that you have, this is what you would get, the 1 minus 4 sine square theta plot. This is the derivation from class. The different dash lines that you have, these are actually experimental results. So, you have a flow past a circular cylinder, you measure the pressure starting from the forward stagnation point. So, this is your forward stagnation point, this is your rear stagnation point. So, you are actually trying to measure what is your pressure profile as you move away from the forward stagnation point. And what you observe is that the pressure profile within some distance from the forward stagnation point is well described by potential flow. But then as you keep moving further away, you start seeing deviations. So, deviations of two kinds. One is obviously that the value of pressure that you are measuring is getting lowered. So, there is a lower pressure that you have. But the other interesting deviation is that the pressure profile is no longer left-right symmetric. If you remember, we had this discussion in class that when you are solving pressure from your Bernoulli equation, pressure is quadratic in the velocity field. So, if your velocity field has a left-right symmetry, that left-right symmetry gets translated also into your pressure field. And actually this is something that you can use to argue that there would be no drag in the problem. If your pressure field has a left-right symmetry for a circular cylinder, and the consequence is that D'Alembert's paradox, which is drag is equal to 0. So, this is where we started actually discussing a little bit more about why viscous effects are important. So, this is kind of the starting point to think in terms of that you have this asymmetry in your pressure profile, and the asymmetry in your pressure profile basically translates to the fact that there is something that is going on near your rear stagnation point, which is not reflective of what you get from your potential flow solution. Because clearly if there is an asymmetry in the pressure profile, that means the velocity profile close to the rear stagnation point is not quite what we see here in the picture. So, but what about other quantities? We have also looked at various other quantities basically being the lift that we calculated in the class. So, we said that there was this remarkable result, which was the Kutazoukowski lift theorem, which gave us that the lift on a two-dimensional object was given as rho u infinity gamma. It does not matter what is the shape of the object. So, for a 2D flow, potential flow past any object, if there is a circulation, and there is a flow past an object, or the object is translating, either way it will be experiencing a lift force. And then we use the Zukowski hypothesis or the Kutta condition to say that how do we decide the value of lift. So, for that we had done a flow past a flat plate, and we said that when we did a flow past a flat plate, there are two stagnation points that are there on the plate, and if you fix the value of circulation such that the stagnation point coincides with the trailing edge, that is how the stagnation point value is going to get fixed. So, if there is a flow that is going from here, you would have streamlines which are going to bend here and go away. So, now if you measure the surface velocity, imagine that you are zooming this into this region, and if you zoom into this region, so this is the rear stagnation point and this is the trailing edge. So, a fluid parcel which is moving along this direction, the velocity at this location we found out to be infinite. At the trailing edge, for a zero thickness plate, when the fluid is turning around, it experiences infinite velocity. By the time it comes to the stagnation point, it should be 0. So, there is an immense amount of retardation that is going on for a fluid parcel that is trying to slide over the plate. And this is basically what we said, that when you are doing this calculation, the value of your lift force gets determined such that the rear stagnation point goes and sits on the trailing edge, and that is how we actually manage to compute what would be the value of circulation and thus the value of the lift. So, potential flow theory obviously gives us this value of lift, but the pressure distribution, would it be this bad if the object was not like a circular cylinder? So, if the object was more streamlined, so this is a symmetric airfoil and you have an angle of attack that is 0 here. So, this is incident along the axis or along the line of symmetry of the airfoil. You have here the continuous line is your irrotational flow theory calculation. This has some effects of compressibility, but the purpose of comparison you can ignore the Mach number written on the slide here. So, you can think of the continuous line here is what you will get from a potential flow calculation. You can do some of these things analytically by exploiting the fact that 2D potential flow can be done in a complex plane. So, there are different ways of using conformal mapping to solve it, but for what is the focus, the continuous line is a solution from potential flow, and the symbols are measurements of pressure or the pressure coefficient here for different locations along the chord. So, x by L are different points where you are making these measurements. So, you make measurements on the top, you make measurements in the bottom, and that is what you actually see here as the symbols, the open and the closed symbols, and they fall nicely on this particular curve. So, this is saying that if the object was sufficiently streamlined, then your potential flow theory would give you a very accurate description of the surface pressure. So, what happened in the problem of flow past a circular cylinder, that the pressure profiles were deviating from irrotational flow theory, that had to do more with the shape, that we were dealing with something that was more blunt in shape, or bluff is the correct way of saying it, is a more bluff kind of an object than a streamlined object. And if you take this forward and now do something which is asymmetric, or rather something that has a little bit of a bend here. So, there is a camber that is there. So, you have, this is known as the Zukowski airfoil, or it is close to a Zukowski airfoil. There is an angle of attack here alpha, and then you compute the pressure distribution. So, there is a pressure distribution in the bottom, there is a pressure distribution on the top. Continuous lines are potential flow, these are potential flow theory results. Symbols are measurements. So, you see again that there is a very nice match between what you get from experiments around 3 million Reynolds number with what you get from potential flow theory. And this also brings about the fact that if the pressure forces on the top surface and bottom surface are not exactly the same, you would expect a lift force, which is something which we already know, that now here there is a corner with an angle of inclination, and if you remember, we worked out for a flat plate problem. So, for a flat plate problem, if there was an angle of inclination, we found out that the circulation that it should develop would be proportional to the incident flow sin alpha. So, there was a circulation that it actually starts developing, which depends on the angle of inclination and the uniform flow, such that if there is a uniform flow that comes in, so that the stagnation point goes and sits exactly at the trailing edge. So, with that you can do a lift calculation, and that is what you have here. So, this is your non-dimensional lift or the lift coefficient, which is plotted as a function of the attack angle, and you have the potential flow theory, and the symbols here are measurements. So, this is something which is quite remarkable, and if you think about it, even until the First World War, aircrafts were quite dominant. By the time of the First World War, aircraft were actually quite dominant. 1903 is the mid-December is when the first Wright brothers had their first flighted experiment that they did. So, since then, it's almost the next 10-20 years, aircrafts were being manufactured, they were being flown in different parts of the world. The calculation of lift worked remarkably well in trying to figure out how they would fly, like what is it that is necessary in order to design these airfoils and how they should actually fly. So, potential flow theory was enough for the aircraft to stay afloat and fly. What it was not sufficient was to give you how long can it fly, because how long can it fly depends on the resistance that it experiences from the air. So, it needs to burn fuel in order to propel itself. So, if you do not know how much drag you are experiencing, you will not know how long it can fly. You can say whether it will fly or not, but you will not be able to predict the duration of flight. So, potential flow theory extensively helped in designing aircrafts, and this is again one such experimental data for the Zhukovsky airfoil, where you have the drag coefficient and the lift coefficient both being plotted. It's a little sketchy in terms of the quality of the diagram, but these are all from, if you want to go back and look, from a book by Hermann Schlichting called Boundary Layer Theory. So, I am just showing you some figures to motivate about potential flow. So, you have the earlier picture that I showed, which was regarding lift. So, lift as a function of angle of attack, and what you get from potential flow, what you get from experiments is fairly in good agreement. So, it is not like potential flow is all useless, you get that quite reasonably well. The part where things go amiss is your drag, because there is no drag from potential flow. So, if you were to make experimental measurements, obviously you will find there is a resistance that you are experiencing. If you have this, if you require this airfoil, so if you need this airfoil to translate, or if there is a uniform flow past this airfoil, you are going to experience a drag, whereas potential flow will clearly tell you that drag is 0. So, this is the beginning of what we are going to do next. So, our discussion that comes about next is primarily it will focus on two things. One is the aspect of drag, and the second aspect, which is also quite fundamental, that is related to this diagram here of the pressure asymmetry, that has to do with separation. So, with this we will get started with discussion of the topic we have now, which is boundary layer theory. So, you have already seen the governing equations that we have been working with, the Navier-Stokes equation. This have been around since the mid 19th century. But there is no general solutions of this equation. You don't have a general solution for this Navier-Stokes equation for any arbitrary initial conditions, arbitrary boundary conditions. In class, we have tried solving this for some specific problems, which leads to two limiting forms that people have worked extensively for a long period of time. One is when you say that viscous forces dominate, which means you can ignore inertial forces. So, that gives you your Stokes equation. So, that is to say that I take the equation for the Navier-Stokes, equate the left hand side to 0, and there is a balance of viscous forces with pressure gradient. Now, what Stokes equation does, it gives you a good description of what the flow looks like at very low Reynolds number. We have learned that Reynolds number quantifies the importance of viscous to inertial forces, or it's another way of thinking about it is the ratio of the flow time scale to the viscous time scale. So, if the momentum diffusion occurs instantaneously when compared with any other time scale in the problem, that means inertial effects are negligible. You can think of the problem purely dominated by viscous forces with pressure gradient. There are no acceleration that is there in the problem. Now, what do you achieve from this equation? So, what you gain out of this equation is you can do a lot of calculations that can be compared with experiments. So, say for instance, there is an object that is of mass m that is falling due to gravity in a very viscous fluid which has density rho and viscosity mu. So, what you can compute is the drag force. So, you can do a calculation of drag force and you can find that if the object was moving with a velocity u, it would experience a drag force that is 6 pi mu a u. So, this is the Stokes drag, and then you can compute what would be the terminal velocity by equating this to the weight of the object, and this would give you a Stokes terminal velocity. So, that would be 2 by 9 delta rho a square g by mu. Delta rho is basically rho p minus rho f, because here this would be the weight minus the buoyancy force that might be there. So, these are things which the low Reynolds number description gets quite well. We haven't done detailed derivation of the low Reynolds number problem, but that is again a regime which is quite well documented and quite well known since the advent of the Navier-Stokes equation. If you have negligible viscous force, you have your Euler's equation, and specifically for the case when we are thinking of the flow having 0 vorticity, we have our potential flow equations. Potential flow equation requires you to solve a Laplace equation for the velocity potential, and this in some sense can be viewed as the limiting form when Reynolds is very large. Now, whether it is truly a limiting form, that we have already seen so far. So, we have seen that things like drag, it won't be able to capture. So, you would not get any drag for steady motion, but it gives you a nice description of pressure variations that would be there in the problem. So, if you are looking for how pressure actually varies around an object, it does a reasonably decent job. It is not too bad. So, now this is where the story was for up until the late 19th century, and you can see why these problems were extensively studied. The reason these problems were extensively studied is there in the equations. What is so special about the two equations? Both these equations are linear, and both these equations don't have an explicit time dependence that is there in the problem. Whatever is the velocity field, whether in the Stokes equation or the potential flow equation, is described by the instantaneous boundary condition. And this comes about from the fact that you are looking at the two limits of the problem. In one limit, viscous diffusion is never happening, and in the other limit, viscous diffusion is so fast that it is faster than anything else. So, when we studied the unsteady problem, we realized there is a certain time scale it takes for viscous diffusion to spread over a certain distance. So, these are the two limits where you can think of that viscous diffusion is either super slow, it's negligible when compared to everything else, or it is extremely fast and faster than all other time scales in the problem. So, this is one of the two regimes which are extensively studied. But what this gives us when you are coming from looking at problems, especially when you are thinking of scenarios which are very large Reynolds number. So, going back to our equation now, but in the non-dimensional form, this is our non-dimensional Navier-Stokes equation, and obviously all these equations are accompanied by equation of continuity. So, we are dealing with incompressible Navier-Stokes equation. So, when you are looking at very high speed flows, you remember in the airfoil example that I showed, the Reynolds number was of the order of few million. So, if the Reynolds number is of the order of few million, can we completely ignore this term? And that is basically what we ended up doing in a lot of the potential flow calculation. So, we realize that by saying that Reynolds is very large, where you are looking at high speed flows, we are doing this assumption of dropping the viscous forces. And by dropping the viscous forces, we are arriving at a final conclusion that the object can move with any velocity in the fluid and experience no resistance. So, how this got addressed happened in August of 1904, where in a conference, at that point not a very well known person, a 29-year-old Ludwig Prandtl, gave a 10-minute talk. So, especially this is very important because many times we discuss importance of giving a key idea, talking about a key research idea in a short duration of time, and people find it difficult. Prandtl's talk explaining or introducing boundary layer theory was in a 10-minute talk. And then in 1905, he wrote a paper which had 7.5 pages of text. So, he just kind of summarized what he gave in that talk. So, what Prandtl did was phenomenal in a sense of how he went about looking at this particular equation, because clearly at that point in time there was no ability to solve this equation exactly in whatever capacity for keeping the viscous forces. So, you either did a problem which was a Stokes flow problem, or you did a problem which was a potential flow problem. You didn't know what was happening in between, and you have already understood that what is happening in between is important, because if you do the potential flow calculation focusing on large Reynolds number, you are going to actually arrive at these kind of absurdities that there is no drag that is existing in the problem. And obviously, the second aspect, which is a little bit more difficult or a nuanced aspect, is that the aspect of separation, that the flow need not continuously remain attached to the body. So, Prandtl's viewpoint was the following, that you have a surface, there is a flow that is going past this surface, and you have basically found that the Reynolds number for this flow is very large. But then at the surface, you have a no slip boundary condition. So, which means that your tangential velocity at the surface should be 0. So, the fluid should adhere or stick to the surface. So, what Prandtl said is that at the surface, obviously u is equal to 0, if u I call as the x component of the velocity, and far away u is equal to some u infinity. So, Prandtl's viewpoint was the following: if viscosity is very low, you have a very low viscosity in the problem, which means that viscous effects are negligible and it doesn't really travel a very large distance, then the fluid would start from a 0 velocity, but very quickly it would achieve the velocity that is flowing further away. So, u should be 0 at the surface because it cannot slide over the surface. So, viscous effects are going to act at the surface, but then in a short distance you are going to have the flow match to whatever is the imposed or the external flow. This was his viewpoint, that you will have viscous diffusion acting in a thin transition region. So, there is, imagine you have a very high speed flow going over a surface. So, obviously significantly far away from the surface, the flow is whatever the high speed flow that you have introduced. But at the surface, there is no way that the fluid can slide, it has to stick. So, Prandtl's point was that the fluid will stick at the surface and then quickly over a short region, it is going to transition to whatever is the imposed high speed flow. Now, why is this important? Why is this kind of an idea important? The reason why this idea is important is if you now compute what is your shear stress. So, in this case shear stress only has in the picture an xy component. So, the shear stress, if I just focus on the flow being purely in the x direction, will depend on dou u, dou y. And if this transition region scales as delta, then this is mu u infinity by delta. So, Prandtl's viewpoint was that the shear stress that is generated by this action of the fluid going from the velocity at the wall to the imposed velocity over a thin transition region can be very large. This quantity is not small. Yes, you have a viscosity sitting in the numerator which is small, but you also have this transition layer thickness delta which is sitting in the denominator, which can be also quite small. So, you are looking at a ratio of two small numbers. So, unless you know that how delta varies, you cannot dismiss of that term being saying negligible. And this is what is there at the heart of potential flow theory. Because in potential flow theory, what you are saying is that if you write down the force that is acting on the body, the force acting on the body is F equal to sigma dot n ds. And what did we write sigma dot n ds as? We wrote sigma dot n ds is minus P n ds. This is what we did, right? If you remember the discussion on even for added mass or the drag calculation or the lift calculation, we always wrote sigma as just the pressure term. So, yes, you can say that the modification of pressure, if you go back to the picture that I was drawing of Cp, the modification of pressure will look something like this, let us say. Yes, that modification of pressure is going to modify the force. But there is also one part which is missing here, that is the part which is the contribution from the viscous stress or the shear stress. There will be a shear stress contribution that will come in the force calculation. So, yes, correcting your pressure is crucial, correcting your pressure is important, but then if you are thinking only in terms of pressure correction, you are going to arrive at a conundrum when you think of a streamlined object like an airfoil. Because for this object, we saw pressure is matching very well with potential flow theory. So there is nothing to correct there in pressure. When we saw the CP for a flow past an airfoil, it is really doing a great job from what you get from potential flow theory. So don't think of the motivation for doing this purely in terms of correcting your pressure. Yes, for objects which are a bit bluff, there is a motivation of thinking it in terms of pressure also, but the primary motivation for doing all of this is to say that there is a contribution that you are going to get now to your force calculation that would come from your shear stress. You will need to integrate this quantity. So we got a measure of what the shear stress is. You will need to integrate this particular quantity over the surface of the object. This quantity, earlier we said mu E dot or mu E. Previously what we said was that I have my total stress as the following. And what we have been saying so far is that when viscosity is small, let's just happily dump this term. There is no need for looking into this term. Why do we bother? Let's just focus on pressure. Prandtl's insight was, if there is a high speed flow that is going past a surface, the fluid has to adhere to the surface and then the fluid gets a short transition region over which it transitions to the exterior flow. So now if you work this out, you get a shear stress which is not guaranteed to be small. It can actually in fact be large. And thus this part which was earlier erroneously dropped needs to be brought into the picture. And this is exactly how he motivated the problem. So this insight of Prandtl, and there is a lot more in that paper, and I will strongly encourage everyone. It's one of the easiest paper to read which has such a fundamental concept. It has barely few sets of equation and then some experiments in the end. The English translation is also available on the web. It's originally a German paper. But if you read it, you will realize how he goes about explaining what terms are important. Because when you look at this equation at the outset, we kind of take it for granted what Prandtl's equations are. Because we look at this equation, you can't necessarily say that what terms are actually going to be important, what terms are going to dominate. It appears a bit like magic. And this we will, by doing all of this, we will actually come across a method of doing this kind of problems. And when Prandtl did all of this, that method in a formal sense was not there. So let's see, we will get started a little bit and then, okay, maybe I'll just do it. So I'll write down the equation for a two-dimensional flow, and what I'll do is I'll assume this to be in steady state. So you can make modifications for unsteady effects. We have already looked at what unsteady effects does in viscous flows. So we'll kind of treat them separately right now. So you have figured out how unsteady effects come about in flow. Now we will look at steady flows, but where the acceleration term is not necessarily 0. And Reynolds, I'm going to write it as epsilon. So this is a problem which is very high Reynolds number. So Reynolds is defined based on some incident flow, some large length of the object, let's say the size of the plate, some long dimension that you have for the object, and the kinematic viscosity, and this is a very large quantity. So I have an object like this is x, this is y, there is a u infinity that is incident on the problem. I'll have u dou v dou x plus v dou v dou y equals minus dou p dou y plus epsilon dou square v dou x square dou square v dou y square. And there is a third equation which is dou u dou x plus dou v dou y is equal to 0. Now how did you arrive at this non-dimensional equation? You arrived at this non-dimensional equation by saying that the non-dimensional variable u star is some u infinity into, sorry, the non-dimensional velocity u star is u divided by u infinity. The non-dimensional velocity v star is v divided by u infinity. The non-dimensional distance x star is x divided by L. The non-dimensional distance y star is y divided by L. And you have chosen a pressure scaling which is P. P star is P divided by rho u infinity square. This is how we have arrived at this scaling. And then I have dropped all the asterisks in the equation. So, this is a non-dimensional equation. We first write them in terms of all the starred variables and then I am dropping it for the purpose of convenience here. So, this is where if you now say that I take the limit of epsilon going to 0, you recover steady Euler's equation, which would be the starting point for doing a potential flow like calculation, and that is basically the problem. So, Prandtl's approach is to say u star is u by u infinity, x star is x by L. So, the fluid velocity in this direction is scaled by the incident flow. Distances in this direction is scaled by a length L. But let us assume that the velocity in the vertical direction, the one which is perpendicular to the plate, has some scaling. Let me just use, let's use alpha. So, alpha u by u infinity and y star is delta y by L. So, what I have done here, I have put some factors in front of the scaling of v star and y star, saying that they do not necessarily scale with u infinity and L. Now, how do I find these factors? How do I obtain what that factor actually should be? So, for that I go back to the equation. So, if I use this non-dimensionalization, then dou u dou x remains dou u dou x, but dou v dou y will become alpha by delta dou v dou y is equal to 0. Your governing equation was dou u dou x plus dou v dou y equal to 0. Now, you non-dimensionalize it using these sets of variables. So, these are actually all starred variables. So, when you non-dimensionalize them using these variables, you arrive at this. Now, what should be the relation between alpha and delta? Because if alpha and delta depends on epsilon, then how should they depend on epsilon? So, we want mass conservation to be valid. So, if there is any choice of alpha delta which makes this quantity either order epsilon or smaller, that means I land up with an equation which is dou u dou x equals to 0. That means the fluid velocity along the x direction does not vary at all. I get a constant fluid velocity, right. So, to have mass conservation being satisfied, I need alpha to be equal to delta. That is the only way I can have satisfying the condition for mass conservation. That finally, my non-dimensional variable is u star is u by u infinity, x star is x by L, v star is delta u by u infinity and y star is delta y by. this will satisfy mass conservation. So I will have a balance between dou u dou x and dou v dou y. Now let's go to my governing equation, which is the x momentum equation. So if you want, we will write down the non-dimensional and then maybe come to the dimensionless version. So if I scale u by u infinity, so that is u infinity by L dou u star dou x star. This is, sorry, this was, this term is not there. So I have rho u infinity into u infinity by L u star dou x star plus v is delta u infinity v star, and this is u infinity by, yeah, this relation delta by L so I have this should be V. So V is u infinity by delta into V star, and dou y will be delta by L u infinity dou u star by dou y star. Yeah, this is V by u infinity. And then for pressure, I will have 1 by rho u infinity square into 1 by L dou p star dou x star plus mu u infinity by L square dou square u star dou x star square, and for V will be u infinity by delta, and y will be L's delta square by L square dou square. Okay, hang on. This is dou square u. So this is dou square u dou y square. So that would be delta square u infinity by L square dou square u star dou y star square. So this is what you have now. So now if I take out rho u infinity square by L, rho u infinity square by L will be u star dou x star plus v star dou u star dou y star is equal to minus this is L, this is rho u infinity square. P star is P by rho u infinity square. So here you have rho u infinity square by L dou p star dou x star mu u infinity by L square dou square u star dou x star square plus delta square u infinity L square dou square u star dou y star square. So these are what you obtain here as your governing equations. So now if I cancel out the terms, I will finally get u star dou u star dou x star plus v star dou u star dou y star is equal to, if I write this, I should get rho u infinity L by mu dou square u star dou x star square plus delta square dou square u star dou y star square minus dou p star dou x star. So now if you look at this equation, the term that is sitting here, that is your epsilon or 1 by Reynolds number. So now if you just drop that term by saying epsilon goes to 0, then automatically you would arrive at the inviscid equations. There would be no change whatsoever. Now inside in the viscous term, there is one term which is dou square u dou x square, and there is one term which is dou square u dou y square, which is multiplied by delta. Now what is your delta? Delta here is basically giving you the modification to your length scale in the y direction. So L is the length scale variation, non-dimensional length scale variation in x direction. In the y direction, it is L by delta is the length scale. You can write this as L by delta. That is the length scale variation that is occurring in the y direction. So Prandtl's idea is that the transition region that you have is very small. So the transition region is very small. That means that scale that I have chosen here, delta, should actually be very large. So the final idea is so there is a term here which is epsilon dou square u star dou x star square plus delta square epsilon dou square u star dou y star square. So for the viscous term to be there, this term delta square epsilon should be 1, which means that that factor in the vertical direction will scale as 1 by root epsilon or root Reynolds number. So the final conclusion is you have a length scale here which is L and a length scale in the vertical direction which is L by square root Reynolds number. Okay, let's stop here. It has to be a quantity that is order 1 because you want it to be balanced with the other inertial terms. So which is why you can choose it to be any constant. So you choose it to be something that is an order 1 value so that it is of the same magnitude as your inertial terms in the problem.